Hello, welcome back everyone. It's our penultimate session now, and it's great to have with us a speaker, Dr. Rui Alves, and he is talking today from Blake Clough Consulting, and talking on the topic of sub-synchronous oscillation studies. So over to you, Rui.
Hello everyone, thank you for attending the presentation. So my presentation will be about subsynchronous oscillation studies, needs, approach, and challenges. Firstly, I'm going to briefly introduce our company, then go over the theory about subsynchronous oscillations, and afterwards how are subsynchronous oscillations studied in terms of NESO, so with regards to Great Britain, and then mitigation strategies which can be applied to mitigate such oscillations. So about us, Blake Clough is a consultancy. We are specialists in electricity networks. We are helping in the decarbonization of our energy network and slow the climate change while balancing costs and benefits for consumers. We have a strong track record and we've been growing steadily since 2021. We started with 3 persons in 2021 and are around 60 just now in 2025 in 4 different locations. We work in a wide range of capabilities across the electricity sector, as you can see. We carry out power system analysis and support developers with grid connections. We lead projects on curtailment analysis and actively driving electricity network innovation, and also supporting the design and development of offshore wind farms, HVDC projects, CP 2030, and also our new service with regards to energy yield assessments. So what are subsynchronous oscillations? I think that before I explain what they actually are, what this phenomena is, it's important to step back and think about the environment in which they occur, which is essentially in a power system. Power systems are incredibly complex. They aren't just made of individual components, but of many interconnected elements that all interact dynamically. So when we look at a power system like this one, for example, which was, it's a simple plot of a power system, you can already see that it's inherently complex. There are so many components here. There are synchronous generators, wind turbines, there are residential load clusters, distribution, there's transmission links, there's HVDC links, there's shunt compensations, offshore wind farms, HVDC cables, etc. So there are many components which are interacting together. Sometimes these interactions are benign, so they don't cause any harm to the network. However, in other cases, they can lead to oscillations, resonances, or even stability issues. Yeah, so this complexity is what makes studying and managing modern power systems such a big challenge. And this complexity is not only visible in a bigger scale, like I was showing before. If you look, for example, at this plot here, where you can see basically a one-line diagram of an offshore wind farm, you can see already that there are many elements involved here which can cause such interactions. We have wind turbines and converters, offshore and onshore substations, export cables, shunt compensation, and loads, which are all interacting within just one project. Each component has its own dynamics, and then the interactions between them can cause phenomena like resonances, harmonics, and oscillations. This is to say that whether we are looking at the whole power system, like the previous slide, or for a single connection point or a single plant, just like in this figure, the underlying story is the same, is that multiple dynamic components interact in complex ways, sometimes leading to unexpected behaviors. And on top of that, even the control systems that manage wind turbines in this particular case, but these controllers that you can see here, these diagrams, are also used for all the other inverter-based resources, such as solar panels or battery energy storage systems. So these controllers that I used add another layer of complexity. Controllers are constantly adjusting voltage, frequency, and power flows. And while they are designed to stabilize the plant. In this case, it would be to stabilize the offshore wind power plant and all the transmission system until the electrical network. Their interactions with the network can cause somewhat harmful interactions, harmful phenomena in the network. Which brings me to the next slide, where we can see the different types of dynamic phenomena that emerge from such interactions. In this chart, you can see that there are several timescales. We have electromagnetic wave phenomena, for example, like lightning surges and switching events. Then if we move into the millisecond range, we encounter inverter-based control dynamics and SSO resonances, where machines or converters interact with the network and frequencies below the system frequency. So it can be seen that there are lots of phenomena that can happen in a power system, and the root causes are completely different. The point is that the power systems are subjected to a whole spectrum of dynamic behaviors, each operating on a different time scale. Some of these are well understood and controlled, while others, like the synchronous oscillations in modern converter-rich systems, have become increasingly important to study today. So what are subsynchronous oscillations? They are pretty much oscillations at frequencies that are less than the power frequency, which in the United Kingdom is of 50 Hertz. They are caused by interactions between components of the power system. Initially, they were known to be caused by series compensated lines and generator shafts. However, throughout the years, it has been seen that inverter-based resources and its controllers are also causing this oscillation phenomena. And if left undamped, they can damage equipment. The generation can be disconnected from the electrical grid, and the worst case scenario, obviously, is loss of supply and blackouts, etc. These blackouts, which can be partial or local or fully on a larger scale. This type of oscillations, they are not new oscillations. They haven't been found recently. The first time that they were seen were in the 1970s, actually, in the United States, where you can see in this picture on the right, there's a shaft that is broken. Well, this subsynchronous resonances led to mechanical failure of turbo generator shafts, and that triggered global awareness of the issue. So this was in the 70s initially, but today the picture is more complex, as you can see in this plot here on the right, and as shown in the diagram. SSO is now considered a family of different phenomena. On the left, we still have the classical SSR categories, which were presented in the previous slide, for example. And on the right, you have the ones grouped under PEDI, so power electronic device interactions, which include control interactions between converter and the weather network, or between multiple converters interacting with each other. So when we talk about subsynchronous oscillations today, it's not just about classic synchronous generator problems, it's a broader set of phenomena, which includes already converter-driven interactions. So why does it matter now? As more inverter resources come online, especially now in the UK and in the rest of Europe, since we are replacing synchronous machine or fossil fuel power plants, we're replacing them with inverter-based resources such as offshore wind turbines or onshore wind turbines, solar panels, etc. The power system is more vulnerable to emerging subsynchronous oscillation mechanisms, especially converter control interactions. So subsynchronous oscillations are not just a legacy issue. They can arise in systems with no series compensation, which was the first issue. I left here in this slide a couple of events that have arisen recently. There's one in Great Britain in August 2019 with oscillations of 9 Hertz, more or less. Then another example was in Australia in November of 2019, where it was in multiple oscillations in a 720 megawatt renewable rich area. Then another one in the United States in 2021, in a large solar PV farm. And then lastly, in Great Britain in August 2021, so this was in the north of Scotland, subsynchronous oscillations in around 8 to 9 or 10 hertz were sustained for quite a period. There were two separate occasions, around 30 minutes apart. Interesting enough, these oscillations in Scotland, which is the slide that I'm going to show next, they were mitigated after synchronous plants were resynchronized to provide additional damping. So what you see here in this figure is exactly what a synchronous subsynchronous oscillation looks like. They are oscillations that occur at frequencies below the nominal system frequency, as I said. But in this chart or in this snapshot of the SSO, what you see is that initially the voltage is at a specific level, and then very suddenly there's an increase in the voltage level. On the zoomed in plots at the bottom, you can see how the oscillations build up quickly, reach significant amplitudes, and then they fade away again. And they faded away because of the introduction of damping from the synchronous generators. Now, these are the kind of oscillations that are undesirable because they place additional stress on equipment, and this can cause protection systems to trip, and in the worst case, may threaten system stability. So how exactly are subsynchronous oscillations studied in the UK? So NESO has some guidelines just now. And as you've seen previously in the previous slides, what I've shown, this is a recent event when it comes to inverter-based resources. So NESO was looking at the past, at lessons learned. They thought, okay, we need a methodology, we need a guideline to study these oscillations. Because the system risk is changing. So there's an increase of penetration of inverter-based resources. The converter control interactions can cause oscillations from a few hertz to hundreds of hertz. So it's still not exactly known what kind of bandwidth we are dealing with. And especially because assets had to be retuned and phased back to maintain stability. Short circuit level alone, which was an indicator that has been used for a long time to prove how strong or weak a network is, proved insufficient as a risk indicator. So yeah, all this led to the need for consistency and compliance. And before 2023, there was no formal process for subsynchronous oscillation compliant, and therefore developers faced lots of uncertainty. They didn't know exactly what tests they would need to run, what models to provide. So NESO came up with a first guideline that standardizes the study scope, modeling requirements, and acceptance criteria, with the overall aim of protecting the network security and connected assets, and provide developers with clear expectations before they energize or they are connected to the network. However, just a couple of days ago, there was an updated approach on the subsynchronous oscillation studies. So it's still an ongoing process from NESO. It's still evolving. So the first step was the interim scope in 2023, which here is mentioned as the earlier approach. This scope provided a baseline set of requirements or of studies that developers needed to provide to NESO to then be able to connect to the electrical network. And the studies are mainly electromagnetic transient, so EMT step tests, frequency scans, and injections, with eigenvalues analysis as optional. This was applied fairly broadly and was more sort of a one-size-fits-all approach. But a couple of days ago, NESO shared the presentation. They had a webinar where they started targeting more the differences between grid following and grid forming converters, which are the type of converter controllers that inverter-based resources use to connect to the network. It also sets clear requirements depending on the connection type. So that is basically the type of converter that is used in the wind turbine. It's even if it's a full-scale back-to-back converter, for example, or a DFIC converter. It also standardizes the use of a specific tool, so PSCAD, MHI. Overall, the methodology is becoming more refined, more system-oriented, and more tailored to specific technologies being connected. And now I'm just going to show in the next slide some results that Blake Clough Consulting can provide, specifically for the EMT step tests, the small signal injections, and active frequency scans, which are the mandatory tests that right now are in place and the developers need to show to connect to the network. So the first one is the step change, the electromagnetic transient step change. This test is required to check the plant stability and dynamic response under sudden grid voltage disturbances. The plot on the right shows the response of the plant to a 5% voltage step under the condition of full active power output and zero reactive power. So if you look at the plot, you can see the first plot shows a step of 5% in the voltage, keeping the frequency at 50 hertz. Power starts at 50 megawatts and then jumps at 11 seconds when there's the increase in voltage. The reactive power starts at 0 and then drops. So pretty much overall, this result demonstrates a stable and well-damped response to the step test with no sustained oscillations. So this is the kind of behavior we want to see in compliance studies, as it shows that the control system is robust against sudden grid voltage changes. And as you can see in these bullet points here, we are looking at a response that settles in 2 seconds with no uncontrolled oscillations or instabilities. And this is what we are seeing in this plot. The second study is the small signal injection, which is required to test and identify oscillatory modes and assess stability margins across a frequency range. This is pretty much we need to add this disturbance to the model. So the small sinusoidal perturbation needs to be added to the model. It's a sweep of 1 to 100 hertz, and for a big voltage angle, for a voltage angle of 1 to 49 hertz sweep. The plot shows the results of this small signal injection under a perturbation of 10 hertz, this specific one. At the top, you can see the voltage waveform with and without the plant connected. So there are 2 lines there. The injected oscillation is visible, and the comparison shows how the plant interacts with the disturbance. The frequency trace shows a corresponding 10 hertz ripple around the nominal 50 hertz, indicating that the system is responding to the injected signal. But the key takeaway here is that for this particular 10 hertz frequency, the plant interacts strongly with the network, as you can see, from around 10.25 seconds to 11.25. But in this case, the oscillations are well damped and do not persist once the excitation is removed, showing stable behavior. So at 125, more or less, when the disturbance is removed, the system goes back to normal. Once again, it can be seen that the system is well damped and there are no oscillations after the perturbation. The final test, active frequency scan. So this is to identify resonance points and frequency ranges where the plants may amplify oscillations. So this is again a case of injecting sinusoidal signals across a frequency sweep at the point of connection. What we're looking at is the plant impedance as seen from the point of connection. The resistance, reactance, magnitude, and phase are plotted across the frequency sweep. A key requirement here is that the plant resistance should remain positive throughout the frequency range, which here we see negative somehow. That is a warning sign because it indicates potential subsynchronous oscillations that will need further investigation. But in this case, having this result and then comparing with the previous studies, we can see that for these particular frequencies, there are no issues. However, so we cross-check with other studies and we see exactly that it is fine. So while the scan highlights areas of interest, the combined analysis show that the plant remains stable. So mitigation strategies. We looked at a range of studies that NESO asks for the developers to show. And now we are going to look, before I go into mitigations of synchronous oscillation techniques. There are basically two. There are the traditional mitigations and the modern mitigations. Traditional mitigations, which is, for example, the one that was used in Scotland previously, was to turn on a synchronous machine that would provide damping to the system. However, nowadays, there's more things that can be done, such as, for example, tuning of converter controllers or adjusting phase lock loop parameters, for example. Add converter control bandwidths or different control bandwidths, add FACTS devices and compensations, variable shunt reactors, and dedicated damping controllers. Well, thank you so much. I hope you enjoy the presentation and here for any questions.
Brilliant, thank you. Yeah, I was just about to jump in and say 4 minutes, but yeah, perfect that you got to that point. So for those online, just a reminder that the Q&A platform there, if you have any questions on that. Yeah, for me, great to see a more technical presentation that we've had from today, which is really yeah, adds a bit more depth to it, make sure that we're all expanding our knowledge. So a couple of questions just to get us started on this piece. So you mentioned in your talk just then around you found some compliance issues with some of the SSO studies. You mentioned some of the mitigations in that final slide, is that right? And then what ones would you kind of prioritize out of that mix? What are the core mitigations you would put in if you had to choose just a couple?
Yeah, apologies. I think I went too fast on the mitigation strategies. It's because I saw that the 20 minutes have gone.
Sorry.
If I could choose here,
yeah,
I think that the best methodologies just now are to use converter control strategies. I mentioned, for example, if you see the second the box on the right on the top, I have their converter control tuning, and this is because the way that the inverters interact with the electrical grid just now is very different on the way that synchronous machines in the past would interact with the network. Because the dynamics of, for example, a wind turbine are very different from large generators. They don't have enough inertia, and they use inverter-based resources, for example. So they use converters to control the way that they interact with the electrical grid. So if I was to choose a way to mitigate that wouldn't be costly, for example, wouldn't need to add synchronous generators or fossil fuel plants back on the net, I would go for a converter control tuning because it's an easy way for converter control engineers just like myself to get online, control, change the software, change a couple of parameters, and try to understand exactly how we can modify the current and voltage control bandwidths to avoid overlap with network resonance frequencies. So that would definitely be my options.
Brilliant.
My favorite option.
And just so that would be kind of mitigation from the developer side, is that right? What mitigations or recommendations would you make to the to grid providers?
Well, to grid is more difficult, isn't it? Especially because there's so many developers wanting to connect right now that are trying to connect inverter-based resources like battery energy storage and solar panels and offshore wind farms, etc. From that particular case, NESO couldn't just go and change all the controllers all the time from different developers, so they would need to install something in the network, some sort of equipment that would compensate for that specific bandwidth, for that specific frequency of events, which in this case, as I mentioned previously, is below that 50 hertz frequency. So in this particular case, I would have FACTS and compensation devices. So it's devices that compensate for reactive power and voltage. for example, thyristor-controlled series capacitors or STATCOMs, SVCs, which can have damping control loops tuned to SSO frequencies. It can also be the fact of including variable shunt reactors as well, or capacitors to shift resonance points.
Brilliant. Okay. Well, thank you very much again for the presentation and for everyone online as well.
Thank you.